Hi everyone. Today I'm going to show you a little demonstration of facts we learned in sections 3.7, 3.8 when we were doing vibrations of the mass on the spring. I'm going to start with free undamped vibrations. I can actually control in this application damping. I control the frequency of the system. I'm not going to change it. I'm just going to use the frequency which sits over here. And I can also control the mass and the constant. Here I'm just going to keep them as they were set originally. Okay, so it allows also to shift the mass and give initial displacement to the mass. I cannot give initial velocity to the mass. Only one thing I can control is initial displacement to the mass. Okay, so we are going to start with a case of no damping, and I'm going to displace a little bit my mass. I don't know, maybe something like this, up to 4, and let it go and see how the position graph versus time is going to look. Here we do have the same mass vertically. Normally it's horizontal, right? But for our purposes, it's going to be better to see it like vertically this way. On the right side, we can put a graph of position, which is like position of center mass of the mass, and versus time. Time is on horizontal scale. Okay, let me start it. Go a little bit below the screen. I think I should not give such a big amplitude. But you see, that's just sinusoidal oscillations. Remember that when we consider undamped vibration, we do have actually homogeneous solution which consists out of sine and cosine, and I did teach you how to combine them into one sine or one cosine. You see that actually it is one sine or one cosine, one sinusoidal function. You cannot tell that it's a sum of two functions, right? Well, that's just like how it's supposed to look. And I think I'm going to stop it and try to show you some damping over here. So I'm going to put light damping here. And I think I'm going to shift my mass back to 4. And you will see how damping is going to change everything. Sorry, the point sits over here. Well, I think we are going to see the picture anyway, though it's going to just appear a little bit later. Light damping is making our solution changing amplitude, right? If before we had a constant amplitude, now you do see that amplitude is changing actually exponentially, right? And eventually it goes to 0. And well, it goes to 0 faster or slower, depending on how big is damping, right? Let me stop it, and I'm going to kind of change my damping from light damping to critical damping. And let me move the mass again. Well, I think what I'm going to do, guys, I'm going to just restart. I don't want to have the point sitting very far right. Okay, let me put the mass back to 4. And you see, I use critical damping. How the picture is going to change? Well, the picture is going to do no oscillations at all, you see. Critical damped vibrations are going to be just like the sum of two exponential functions. Now, okay, I'm going to stop it and redo it to heavy damping, which is more than critical damping. The picture is not going to be very different. That's just like for you to understand that there's almost no difference between critical and heavy damping. And heavy damped vibration is also going to just stop without making any oscillations. Okay. Now we are going to introduce a force. We introduce force here they don't give us lots of control of force, but we can change the frequency of the force. I'm going to use the frequency of the force 0.1. I want to make on purpose frequency of the force different from natural frequency of the system. Natural frequency is 0.16 hertz and the frequency of the force is 0.1. Here I'm setting it up. Now I'm going to move to no damping case and put my object back over here, and let's see how oscillations are going to look. You see that oscillations are not having same amplitude. They don't even look periodic. They are actually periodic, but the period is not one like move up and down. It's actually going to be several of them. Let me move it a little bit in the middle. So, well, you see that we have kind of two small oscillations, one big oscillation. Why does it happen? Actually, here there is nothing to kill homogeneous solution. Actually, normally in normal life, homogeneous solution is killed with damping, and we do see only steady state solution, which is forced response, which is produced by the force. But here there are two solutions represented, homogeneous and solution which is produced by the force, external force. Because force and natural frequency of the system are different, they're just going to be the sum of two functions. For example, like sine and like another sine with a different frequency. And when you add two sinusoidal functions with different frequencies, you are going to have something like this. Okay, so it does not mean that the picture is not periodic, but the actual period of the picture is going to be much longer. Okay, let me stop it and just add a little damping over here, light damping. Let's see how light damping is going to change the system. Give me a second, I guess I'll need to grab the mass. Instead of grabbing the mass, I'm changing my picture, which I don't want to do actually. Just give me a second. Mass is below. I cannot catch it. Okay. Okay, let me just restart it. It will put the mass back in the initial position. So I'm using now light damping, same natural frequency 0.16 and same force frequency 0.1. Let's see how everything is going to change if we do have light damping. Sorry, I forgot to shift the mass to position 4. I'm going to restart it. Okay, I'm sorry. I just shifted it, but somehow it put it at 0. One more second. Somehow I'm supposed to shift it after I set up the force. Okay. Okay, so let's see how it's going to look. Well, first, guys, it's not going to look very nice. It's going to look very much like what we've just seen a minute ago, right? Unstable oscillations. But eventually, with time, damping is going to kill homogeneous solution, and the only solution which is going to be represented is particular solution. And particular solution is going to be just a nice sinusoidal function. It's almost stabilized. We are going to wait maybe like 3-4 more periods. You are going to see that amplitude stop changing and the period stop changing. So the first part was a mixture of homogeneous and non-homogeneous solution, particular solution, and now we do have only particular solution, which is called steady state solution. You see that long time after the motion began, we see stable solution. By the way, I did not explain how do they make actually this force working. You see that the gray rectangle is moving the suspension point actually. That's how they apply the force, by moving the suspension point. Okay, I'm going to stop this and kind of change damping from light to critical damping. And the only difference for us is going to be that stable solution is going to appear faster. Another difference is going to be that the amplitude of the solution is going to be smaller. Let me list what I want to put the point back. Give me a second. It's not allowing me to change the point. Okay, I'm going to just restart it. First, we set it up to 0.1. Second, I'm going to shift the mass. So guys, you're going to see that stable solution is going to start working faster. And the second thing, the amplitude of this stable solution is going to be much smaller. See? Basically, guys, solution stabilizes after like 2 periods. But you see how amplitude is smaller with critical damping. The case of heavy damping is going to look very same way. I'm not going to consider it. I want to consider what is going to happen with amplitude if we kind of change the frequency. Okay, you see? I'm going to stop it. So solution stabilized. We do see right now only particular solution, and a homogeneous solution died already. Now guys, what I'm going to do, I want to show you what happens at resonance. To do this, I'm going to set up light damping, because there is always some damping, right? And let me change it back to initial position. And let me show you what was happening when the frequency was 0.1. 0.1 is close to 0.16, but it's still like there is some difference, right? We just seen it, but let me show it one more time. So initial amplitude is 4. I'm going to start the oscillations, and you are going to see that eventually we are going to have a stabilized solution. Well, it's going to take like about 70 seconds on this scale. It's not going to take 70 seconds probably like for us, but on this scale, it's going to take 70 seconds. Maybe it's going to take 70 seconds for us too, because it looks like 1 minute almost. Well, solution is getting stabilized. What is also important to understand, guys, the amplitude of this force response does not depend on initial conditions. Maybe I should show you like that for a smaller amplitude or no amplitude. We're still going to have the same amplitude. Maybe I should. So force response is going to produce amplitude which depends on the force and on physical parameters of the system. It's stabilized already, right? We see that amplitude is about like 2 meters, well, considering their scale. Okay, a little bit less than 2 meters, right? I'm going to stop it. Now, to show you that it does not depend on initial conditions, I want to change initial conditions so you can see that it does not depend on initial conditions. So I'm going to place the same force, frequency light damping, and I'm going to put initial conditions like this. I'm going to make it 4 times less. It was 4 initially, 4 meters. I'm giving 1 meter only. Let's see how the picture is going to be different. I'm sorry that it takes a longer time, like long time, to set up these oscillations, but well, because we changed amplitude, the 2 functions are going to give us a different sum originally, but we almost have steady state solution. It's like maybe 2 more periods and we are going to have. Do you see that amplitude of steady state solution is again about like 2 meters? A little bit less, something like maybe 1.5 according to their scale. So no matter that we made a smaller amplitude here, it's still the same amplitude for the steady state solution. So answer for steady state solution does not depend on initial conditions of the system. System is just going to oscillate following the follow the force. Okay, now I'm going to change my frequency a little bit. Make it 15 and start it. I'm sorry, I did not put it the same amplitude, but we already know that amplitude does not affect steady state solution, so it does not matter actually if you started from 0 position or from 1 or from 2. Eventually steady state solution is going to just appear. Do you see what happens to the amplitude? amplitude was increasing in the beginning. And if I started it with 4, it would probably increase less. But eventually, it's going to stabilize. You see, it was increasing, increasing. Now it's stabilized at a certain position. And now we are at like steady state. Why that's such a difference? We did not change damping, right? All physical stuff is same with the system. The only frequency of the force was changing. Well, remember that amplitude depends on the frequency of the force, right? We just did the formulas. Let me stop it for a second. I'm going to change frequency a little bit more. I'm going to just put it like 16. Remember that the resonance frequency is close to natural frequency. Let's see if it's going to make the amplitude even bigger. Well, again, because initial conditions are not changing, nothing here. I'm not going to set it up to 1. I just want you to see the comparison between slightly different frequencies. You see that frequency closer to natural frequency and the amplitude is getting bigger. Because we still have light damping, we are not going to get infinite amplitude, but it's essentially bigger than it was before, right? Remember when we were having 0.1 for the frequency of the force, it was much smaller. And just you see comparison, right? The amplitude for 0.1 is like maybe 5 times smaller than what we have in resonance. Okay, so I'm going to move a little bit further away from the natural frequency. I'm going to just step away 2 units, not 2 units, 200. So let me stop it. And I'm going to put instead of 16 here, 18. So on the other side of resonance curve. Sorry. Well, again, you see that the curve is a different color, but you're also going to see that amplitude is smaller, you see? Because my yellow curve was 1/100th away from resonance. The amplitude was still big enough, you see? But purple amplitude is very close to what we have at 0.1, right? So resonance peak actually is very sharp. So we just stepped a little bit, like I think 10% of the frequency away, and it's essentially affecting the amplitude. Well, I'm thinking to make it like I'm going to stop it and I'm going to have it like essentially bigger, like 25. And let's see how resonance is going to change. You see that frequency is not essentially bigger, but because we still see these oscillations, but the amplitude is already much smaller. And we are getting steady state solution, I guess. And it's very, very small. We are far away from resonance. Even our previous solution at 0.1 is bigger than this one, right? Well, major reason when you push the system too often, it does not have time to absorb energy. So it's like you're pushing in one direction and immediately pushing in opposite direction. System actually feels like you are not doing nothing to it. And you see that amplitude almost like going to 0. Well, I'm not gonna do more curves. It's just like different colors here show like different size of amplitude depending on the frequency of the force. And far away, it's very small. Of course, we can make it smaller, but I don't think that it makes sense to kind of consider more. Well, I'm hoping that you kind of like this demonstration. I'm going to give you a link on this program so you can try to experiment with it yourself. I think it's available online. And again, that's University of Singapore. I don't remember the name of the guy who wrote the program, but I'm going to give you a link and I'm going to write down his name over there. Okay? Okay, that's all for the demonstration. I'm hoping that you like it.